Hello and welcome to a demonstration and tutorial about nmigen. nmigen is a Python-based HDL. Um, it's also trademarked, which is important to appreciate, and it is open source. So just bear this in mind. So you can use it, but you do have to respect the trademarks, the owner of everything, which is MLabs. Now, a little bit about what nmigen isn't. nmigen is written in Python, but it is not an HDL using a sort of a reinterpretation of the Python language. For that sort of style, you want myHDL, and I will show you that. So what myHDL does is you actually write the HDL literally in the Python programming language, and the Python the Python statements are reinterpreted. The actual language is treated as if it was Verilog or VHDL. And obviously, when you do that, things like multiple inheritance or exceptions aren't going to work, not properly. Exceptions certainly not. Multiple inheritance will be problematic. Classes are actually a little awkward as well, because the concept of classes doesn't exist in Verilog. Now, in nmigen, it's a completely different style. What you do is you use explicit statements to construct an in-memory tree representing your logic, and that is then handed to the nmigen tool, which creates an abstract syntax tree and then morphs that and turns it into Verilog for you. So it's a slightly different style, but it does mean that you can use all of the characteristics of Python, classes, multiple inheritance, yield, all the sort of advanced features that you would expect. Oh, and mix and match with say, for example, reading CSV files or reading code or doing for loops in Python that generate code, which you can't do. You cannot do that in myHDL because the myHDL is literally translating the Python syntax directly to Verilog. So here's some links on tutorials. There's quite a few, and one of the things that I found, I trained as in electronics and PCB design, so I'm used to schematics. And I found that if you use yosys to do a show or show top or a show module name, you get a 2D visual representation like this of your program, of your HDL. And I found that it's very much easier to relate that back to the nmigen program. But it took me about 6 months to get used to. And now that I don't need to do it any longer, but I still occasionally will look at it just to check the efficiency, the gate count and so on. Here's a very nice, very simple tutorial which uses again the signals and uses GTK wave and so on. This is we're running off of GitLab, so it's gitlab.com/nmigen, and you can see it's divided down into four main repositories. The actual nmigen tool itself, which contains both a simulator in Python and the actual the actual HDL translation system. nmigen boards contains board definition files for various different FPGAs, and we're also adding ASICs board support as well, so that you can use things like Coriolis 2 and OpenLane, OpenRoad. Then the next one down from that is nmigen standard IO, which contains some very basic things at the moment, such as doesn't contain I2C, it contains a serial console and other things. So it's very basic peripheral support. And on top of that, then is nmigen SoC system on chip creation. So that contains things like definitions for wishbone bus, interconnect, management of peripherals, memory mapping, CSRs, etc., etc. So it's quite a sophisticated thing. Now, I'm the lead developer of a project called LibreSoc, and we decided very early on to use nmigen because of the object-oriented nature of Python. If you're going to do a deep dive, high bang per buck thing, there's really no point, to be absolutely honest, in using a language that was designed in the 1990s. It's just ridiculous. We looked for a modern programming language, and that one that was commonly used. And Python is known now by 1/3 of the world's programmers. So hey, what the heck? And this was a crucial factor. We also looked for a large community, and there are several around. My HDL does actually have a large community. We obviously can't use object-oriented techniques, and classes are difficult. There's also PyRTL and several others. We also looked at Chisel, which is also object-oriented, but it turned out to be 20th on the TOB index or something. And I just went, no, not doing it. But one thing that was extraordinarily good in Chisel was the Chisel IO library. And so we created one of the very first things that we did in the LibreSoc project, thanks to sponsorship from NLnet, was to create a pipeline API. And this pipeline API is based on the Chisel IO class. So we also, in fact, actually ported the Q class from Chisel.io directly into nmigen, and wrapped it with the nmigen FIFO API, so it's compliant with the FIFO API. In this there's nmutil is basically, we've added things like a routine for doing count leading zeros, a byte reverse module, a dynamic runtime byte reverse module, which is very, very simple thing, but it's quite important little things that get commonly used. We drop them into nmutil. And on top of that, we've then created an IEEE 754 floating point pipeline, which is where it gets really sophisticated. And one of the things we did with this was we didn't mess about. We used the extensive use of object-oriented programming techniques, and so um, the the classes, the size of the IEEE floating point unit can be divided down into FP16, FP32, or FP64, or FP128, and we simply parameterized it. The only difference, the only real difference between IEEE 754 classes is the size of the exponent of the mantissa, the number of bits they use for a exponent, no, number of bits for mantissa. So we just put it as parameters into a Python object-oriented class, which would adapt as needed, and then did a multiply and an add and thing. So and then for normalization, copied out normalization of the floating point numbers. We separated that out into a class, which was commonly used in the various various pipelines. So that that's where it things going. That's just sort of a quick overview of that. All right. So what I want to do is to actually go into some examples here. Basic. All right, and let's do some explanations of things. So ALU. No, let's have a look at the counter one. All right. So something. Elaborate, comma, signal, comma, module. There we go. That's better. Python 3 ctr.py. There we go. Must help. Python 3 generates t verilog is the TV. So there we go. All right. So let's just have a look at this. Right. So here you can see that there's basically two statements. This is we've got a signal V, which is your input, and you've got a signal O, which is your output. And we've chosen to make those part of the constructor here. A signal, obviously, that will create a signal of, well, width, but the reset value. This is really convenient here. One of the main problems of Verilog is that you can miss things and you end up with non-deterministic code because you forgot to set the reset values. And one of the key things in nmigen was that its behavior of the outputted Verilog should be deterministic. So consequently, every signal, which is it's a class, has a default argument for its reset, which will be 0 unless otherwise specified. So you don't have to worry about that. It happens automatically. And if you really don't want it, you have to put reset less equals true. All right, and that will ensure that you don't have to have that have the reset system automatically generated for you. So let's have a look at these two statements. You have in the elaborate is where it actually generates the actual HDL, and you start off with a module, and you have two domains by default. You can add more, but by default you have two domains. One is a synchronous domain, and the other one is a combinatorial domain. All right, and obviously it's in a synchronous domain, which will be clocked. It's clocked on the rising edge by default. Again, you can add a clock domain which is on the falling edge if you so wish. All right, and So on the rising edge, the next value of v, self.v, will be self.v plus 1. And v is of width, whatever you specify. So if you specify to 16-bit, as is done here, 16-bit here, then on each clock cycle, that will go to the power of width minus 1 there. So it will start off at FFFFF, and on the next clock it will go to 0, and the clock after that to 1, thing for 2 to the power 16 cycles, so 65536. And here, this combinatorial logic simply takes the top bit. Okay, is the top bit. Pythonistas will recognize v brackets minus 1 as taking the bit from the top end of a list, and Signal very nicely gives you a series of bits as if it was a list. All right, so you have 16 bits and you can access them as in indexing. So I could do this. B brackets 5. Yeah, all right. Or I could do this, signal 3, and I could do not colon 3. Yeah, and that would take me to output the bottom 3 bits. Or I could do minus 3 colon, and that would give me the top 3 bits, the top 3 MSBs. All right. So anybody who's used to Python, it becomes really natural and obvious just what's going on. Now, ctr.v. Right, so you see here this main main function here. That's a convenience function for doing generate and simulate on your example. All right, ctr.v, and as you saw here, I ran the command Python 3 counter generate minus t for type, v for Verilog, and it produced me this Verilog file. Source, Libras, GitLab, nmigen, GitLab, nmigen, such examples, basic, ctr.py. Okay, all right. So let's go over this and see if we can relate the module top to the Verilog that it's that's been outputted here. All right, so let's delete the statements, the debug statements, to reduce the size here. Where are we? Is that? Okay, so there's now less code, all right, less lines, so we can see what's going on. Right now, self.v equals reset to the minus 1, so to the power width minus 1, so that's FFFFF. Ah, look, a reg v got created at 16 bits with a 16-bit constant, starting off at FFFF. Hooray! v$next means the next version of v, which is due to the sync domain here. Always at pos edge clock, that's because we're using the sync domain, and the default for sync domain is, as I mentioned earlier, is the sync domain is the rising edge, so that gets automatically generated for us. All right, and where is it? We get, there should be a plus 1 somewhere. Where's a plus 1? Well, there's your reset getting set to there. V equals v$next. Did I go and delete one too many lines? I did. Oh, wait, hang on. Assign. There we go. Assign $2. Yes, I accidentally did one too many lines. There we go. Assign $2 equals v plus 1. Okay, that is a combinatorial version of this part here. Okay, $2. Right, where does $2 get signed? Ah, v$next equals $2, 15 to 0, down to 0. Okay, so within the at the put's edge. So it's a bit of a roundabout route. It's going into a temporary variable, which is for this expression here, self.v plus 1, which then gets put into v.next here again on a combinatorial assignment, which then the v equals v.next on the rising edge. Yeah, okay, so we're getting there. But you know, this is fairly standard practice. If you handwrite Verilog, you actually do your next variables, your next signals combinatorially, and then you put an explicit at always on the clock's rising or falling edge. You will do an assignment thing. So this is pretty much standard practice. It just took a little bit of a while for me to work it out. Apologies for that. And there's your combinatorial assignment to O. And oh look, assign O equals V15, right? Because the counting down from the top from a 16-bit long signal, 16 minus 1 is 15. Cool, huh? All right, so let's do yosys read verilog top.v. Oh, ha, ha, ha. ctr.v. All right, and let's do show top. Oh, I'm going to have to drag that over from another location. There we go. And now we can see the same thing here. I'm going to shrink that down so you can still see the thing. All right. So there's your clock coming in. There is our V. All right, which goes, the top bit goes out to O, so that's that combinatorial output of V there. And then the V plus 1 goes into an adder here, which goes into that $2 that we noticed, which we're taking all the bits of it, which goes into a register, which goes into v$next, which gets sorry, it's still combinatorial v$next to a thing. That's your is your D flip-flops, which goes on the next clock cycle. That's because it's got that clock there. That goes into V on the next cycle, and repeat. So proc opt. I'm just going to do this again, proc and opt, and we should see, yeah, there we go. It's been turned into a D flip-flop. Okay. Right. So this starts to get closer to what the would end up on your FPGA or in your actual VLSI ASIC. Okay. All right. So you've still got clock. You've got that D flip-flop which stores your V, and there should be a reset value. Yeah, there we go. There's a reset goes into that. All right. There's the V, and there's still the output O of the top bit 15. V goes into an adder. All right, and this is still a high-level block as far as yosys is concerned, and that will get turned into things we can actually do a synth, and that will show that as well. All right, and that add result goes back into that combinatorial block there. It's removed feed on next, as you probably noticed now, which goes back in. That goes your input to the D flip-flop. So there you go. Now let's do a synth. And here we can see we ended up generating a 16-bit D flip-flop and a whole stack of XORs and NORs and ANDs and NANDs, which basically is a will be a full adder. Whee! Ooh, that's a lot. Okay, so you end up with individual D flip-flops, okay, 1 per bit, and you end up with a fully fledged 16-bit 60-bit adder done as XOR and NORs and etc. gates. It's kind of cool, this stuff. Let's redo that actually as a read Verilog. Yeah, ctr.v synth ECP5 show top. And this is how you end up with something that's for an ECP5. So these were carry in, carry out blocks. So those are carry blocks things. There's a trellis flip-flop, which is the ECP5 flip-flop block. So it's all there. Most recently, we've actually got there's something called NextPNR Xilinx as well as SymbolFlow, which will do Xilinx FPGAs such as the RTA7, which is really nice. Now, one other really important thing that nmigen can do is formal correctness proofs, and this has proved unbelievably valuable. Let's have a look. Push the grep MSR FHDL star via test LUT test grev. Oh look, it's a unit test. It's a Python unit test. It uses the standard Python unit test infrastructure. Yeah, this is a big deal. This is why one of the reasons we're using it at nmigen is because it uses in Python. You have all of the support infrastructure from Python and standard practices and so on. So this is a generalized reverse function, which one of the things that we want to add to bit manipulation for the OpenPOWER Power ISA. It's being proposed, and so we decided to create a formal correctness proof for it. So what that means is that we can do assertions on the you can do asserts and assumes, but you don't have to go into the messing about of going as low as Verilog or trying to work out how to do the things, how to run the formal correctness proof yourself. You just use assert and assume, and then you just run the Python unit test itself. Python 3 test grev.py, and I believe this one takes quite a lot of time. One of the things about formal correctness proofs is that if you get them, they're extraordinarily powerful, but they can take an inordinate amount of time. The complexity is exponential. It's not uncommon for people to run large formal correctness proofs for 3 months straight at 100% CPU, non-stop. It's just you have to be very careful with them. So you do. Let's see if we can track down the actual. Where is it? Assert. I want to actually find assert. No, I know that the test .py. One of the things that we found very handy in with the formal correctness proofs is to write a simple version of a module, which is very, very obvious, and then to write an optimized version, which is not in the slightest bit obvious, and simply do for all values of the obvious version, assert that they are equals to the exact same value of the less obvious version. And this is incredibly useful way to make sure that you understand what the heck is going on. Because if you know that if you write the simple and obvious version, which is horrible and you would never put into production, but you can understand it by hand, you can check it, and then with the formal correctness proofs, if they pass and you've done a equals comparison of every output and every input to the complex version, if it passes, you have a 100% mathematical guarantee that the complex version is directly equivalent to the simple version. And that is so important and powerful, and it's why people put up with this stunning amount of time that it takes to run formal correctness proofs, is you cannot miss a corner case in a formal correctness proof. You can get the formal correctness proof wrong, you can put in the asserts and assumes wrong, but the point is that the engines, which are very similar to functional programming languages, try very, very hard to find you some combinations of inputs and outputs that is guaranteed to be wrong, and then show you what they are. If it can't find any, then you're good to go. So it's it's very, very cool. Anyway, that earlier was me running LibreSock with the microwatt Hello World on a Digital RTA7 100T using LibreSock, which is compatible. I've been very, very deliberately made compatible with microwatt. So yeah, it's incredibly powerful system. You know, this is a full 64-bit Power ISA 3.0 scalar processor with level 1 Dcache and iCache and a Relics MMU. So yeah, it is extraordinary things you can do with it, and saves. And you can write standard Python program techniques and train even software engineers to write HDL, and that's really the key. So yeah. Anyway, thank you very much. Any questions? Feel free.